In high-pressure systems, forcing a steady liquid stream through a microscopic restriction creates a violent reaction. The liquid explodes into a turbulent, sub-zero mist. This diagram shows the four structural pillars of a closed-loop refrigeration cycle: the compressor, the condenser, the evaporator, and the expansion device. The compressor acts as the pump, generating the pressure differentials required to move the refrigerant. The condenser rejects absorbed heat to the outside environment, and the evaporator absorbs heat from the space you want to cool. Between those massive heat exchangers sits a component small enough to hold in your hand. The expansion device divides the entire loop into a high-pressure red zone and a low-pressure blue zone. Its immediate mechanical function is to restrict the flow of warm, high-pressure liquid coming from the condenser, forcing a sudden and severe drop in pressure. That pressure drop causes a percentage of the liquid to flash into gas. This phase change lowers the saturation temperature of the remaining fluid, rendering it cold enough to absorb heat once it enters the evaporator coil. The expansion valve continuously calculates and meters the exact mass flow of refrigerant required to match the fluctuating heat load of the evaporator. The heat load in a building or an industrial process is never static. Sun hits windows, machinery cycles on, and occupancy changes. The system requires real-time adjustments to refrigerant flow to maintain stability. This diagram tracks the temperature state of the refrigerant as it moves through the coil. To determine if the evaporator is receiving the correct amount of refrigerant, the system relies on a specific metric called superheat. Inside the coil, the liquid refrigerant absorbs heat and boils. The temperature at which this phase change occurs is the saturation temperature. Once all the liquid has boiled away, the remaining gas continues to absorb ambient heat as it travels toward the exit. The temperature of this gas at the outlet is the actual vapor temperature. If the vapor exits at 11 degrees Celsius and the saturation temperature inside the coil was 5 degrees Celsius, subtracting the two yields a difference of 6 Kelvin. That 6 Kelvin difference is the superheat. If the superheat drops to 0, it means liquid refrigerant is failing to boil off completely. That unboiled liquid will exit the evaporator, flood back down the suction line, and destroy the compressor's internal mechanics. Conversely, a high superheat indicates the coil is starved of liquid. The refrigerant boils off too early, leaving a large portion of the evaporator useless, severely reducing cooling capacity and efficiency. Therefore, maintaining this narrow mathematical window of superheat is the sole objective of a dynamic expansion device. This diagram details the internal components of the thermal expansion valve, or TXV. It functions as a self-contained mechanical computer, using opposing physical forces to regulate superheat without requiring electrical power. The sensing bulb is strapped directly to the evaporator outlet pipe, where it physically monitors the actual vapor temperature. Inside the bulb, warming fluid expands, sending a downward pressure onto the valve diaphragm to push the needle open. Pushing back from underneath are two closing forces, an adjustable spring and the evaporator's internal pressure. When ambient heat increases in the space, the superheat rises. The vapor exiting the coil warms up, the fluid in the sensing bulb expands, and the downward pressure overpowers the spring, opening the valve to feed more liquid refrigerant. As the space cools and superheat drops, the bulb cools down. Its internal pressure decreases, allowing the upward force of the spring to push the needle closed, restricting flow to prevent liquid from flooding the compressor. This continuous tug-of-war on the diaphragm creates a highly reliable thermodynamic feedback loop, powered entirely by the system's own changing pressures. In larger systems, the evaporator coil is long and winding. As the refrigerant travels through this extended piping, internal friction causes a significant drop in pressure from the inlet to the outlet. A standard internally equalized TXV reads the internal pressure right at the valve's outlet, the inlet of the coil. Because it misses the friction loss further down the line, it senses an artificially high closing pressure and improperly starves the coil. The externally equalized TXV solves this by bypassing the inlet pressure entirely. By running a dedicated sensing tube directly from the valve to the end of the evaporator coil, it references the true outlet pressure to maintain precise superheat control. Fixed metering devices like capillary tubes have no moving parts. They provide a static restriction and cannot adjust to these shifting pressure profiles or load conditions. As systems scale in size and demand greater efficiency, modern variable refrigerant flow installations utilize the electronic expansion valve, or EEV. The EEV replaces the mechanical diaphragm and bulb with electronic thermistors, a digital controller, and a high-precision stepper motor to dictate the exact position of the needle. Meeting the demands for wider operating ranges and extreme energy efficiency requires mass flow control to evolve from mechanical-pneumatic balance to rapid digital computation. In the field, technicians routinely fall into a specific capacity trap, assuming a 5-ton refrigeration system strictly requires a 5-ton rated expansion valve. A valve's true capacity is a dynamic envelope dictated by refrigerant type, subcooling, and temperature differentials. If the design drops the system's evaporating temperature, the required orifice size shifts drastically just to maintain that identical 5-ton capacity. Selecting a valve based strictly on a single tonnage number without consulting the manufacturer's capacity chart under specific operating conditions will inevitably lead to erratic system performance. When diagnosing a metering issue in the field, mechanical expansion valve failures generally manifest in 2 primary states: stuck closed or stuck open. A valve that is stuck closed starves the evaporator. Suction pressure drops, cooling capacity plummets, and the measured superheat registers abnormally high. A valve stuck too open floods the system. The superheat drops dangerously close to zero, suction conditions become unstable, and compressor damage is imminent. However, moisture or dirt trapped in a filter dryer upstream can severely restrict liquid flow. This creates an unintended pressure drop that perfectly mimics a failed, stuck-closed expansion valve. This logic tree maps a strict diagnostic workflow. Technicians must cross-reference empirical measurements, verifying filter dryer pressure drops, measuring subcooling, and checking bulb placement before condemning a mechanical valve. While the compressor provides the brute force to circulate the refrigerant, the expansion device acts as the precision logic gate for the entire system. Understanding the thermodynamic balance within the expansion valve is what separates parts replacers from true engineering diagnosticians, ensuring maximum capacity, efficiency, and system longevity.